We have all been there. You're staring down the final question of a physics exam. The clock is running out, and your mind goes completely blank on the exact formula you need to solve it. The question is asking you to calculate the time period of a simple pendulum, meaning exactly how long it takes for the bob to swing back and forth one complete time. You know the moving parts. There is the length of the string, the mass of the bob swinging at the bottom, and the downward pull of gravity. But you cannot remember if the length is squared, if gravity is divided by mass, or how they actually fit together on the page. You don't actually need to memorize the formula. You can build it from scratch using a technique called dimensional analysis. Physics equations are essentially perfectly balanced scales of reality. Because both sides of an equation must represent the exact same physical units, we can use that hard logic to reverse engineer the math. We start with a basic assumption. The time period, capital T, has to be some mathematical product of the string length, the local gravity, and the mass of the bob. Since we don't know how these variables interact, we attach unknown exponents to them, calling them x, y, and z. We add a constant k for pure numbers. Next, we swap physical variables for base dimensions. Length is L, mass is m, and gravity is length divided by time squared. Grouping matching dimensions simplifies this into a single set of brackets. This brings us to the principle of dimensional homogeneity. For this equation to be physically true, the dimensional exponents on the left side must perfectly match the exponents on the right. We can begin equating these terms, starting with the mass dimension to find our first exponent, z. Look at the left side of the equation. There is no mass dimension over there, which means its power is 0. Therefore, z must equal 0. In the real world, this tells us something highly counterintuitive. The mass of the pendulum bob has absolutely no effect on how fast it swings. A wrecking ball and a marble on the same length of string will keep the exact same time. Matching time dimensions. 1 equals -2y, giving y equals -1/2. For length, x plus y equals 0, making x 1/2. Plugging these back, the half power becomes a square root. The negative exponent drops to the denominator, and mass disappears. Just like that, we rebuild the core physical relationship. Without the textbook, we used pure logic to prove how length and gravity dictate the swing. It is deeply satisfying that you can derive the mechanics of a physical system just by ensuring the units balance out. But there is one gap left in our equation, that unknown constant, k. This exposes the strict boundary of dimensional analysis. Since pure numbers lack physical units like meters or seconds, this method is entirely blind to them. You cannot deduce k at a desk with a pencil. It has to be discovered through physical observation, much like the early experimental work done by scientists designing the first pendulum clocks. Through that kind of real-world testing, physicists proved that this specific constant is exactly 2 pi. Drop that into our derived framework, and the formula is complete. Dimensions give us the underlying structural blueprint of the universe. But to paint in the final details, we still have to go out and measure the world.